You should have seen from the unit launch that exponential change is always used to model percent change. That is to say that anything that's exponential is the same as being a percent. Now, did you notice that the bouncing ball, it changed by a percent amount each time? That wasn't the same amount, but it was the same percent amount. Well, exponential change will always have rapid increase and decrease that will not reach, did you see this new word, what's called an asymptote? It's an asymptote. It has a silent P, and that is, again, a value that your graph will never reach. Did you see in the M&M investigation that we lost a lot of M&Ms, but we would never, ever technically get to 0 M&Ms. There would always be some amount left. Now, the general form for exponential change, it's a new formula. It's y equals ab to the x. Now, y equals ab to the x is pretty special because for the first time this year, we see x in a new place. X is in the exponent. And you see whenever the variable is in the exponent, you have exponential change. Now, you also will always have a base. The base, given by b, is going to be the factor of change. In other words, depending on the number that we have for the base, it'll then affect the way your graph, the way your equation, the way your numbers change. So the base is the factor of change. We'll talk more about that, but I also want to introduce to you this letter or this value in front of the base. We call it A, and it's going to end up being the starting value. It'll be where the graph, where the equation, where the numbers start. So y equals ab to the x. That's our new formula, and it's kind of simple, isn't it? Well, let's take a look at what it looks like when you start to graph it. First of all, we find out that we can have either exponential growth or exponential decay. Now, when we have exponential growth, you'll discover that that's always going to happen when the base is greater than 1. When the base is greater than 1, we'll have exponential growth. We also learned that 1 plus r can be thought of as the base, where r is this percentage of growth. More about that in a moment. So here's an example of exponential growth. All it has to be is a base that's greater than 1, maybe the number 2 to the x. So 2 to the x is going to represent exponential growth. Why don't we take a look at what this would look like when it comes to a table of values. Now all we got to do is plug in each of these x values for x. So maybe we plug in -2. Now when you plug in -2, you kind of get this strange exponent. It's a negative exponent. We did talk a little bit about that in the last chapter, that would be equivalent to thinking of this as 1 over 2 to a positive exponent. And so the positive exponent now would allow us to do 1 over 2 squared, which we know is the same as 1/4. I already plugged in -1 for you. What happens when you plug in 0? You get this strange exponent of 0. Now 2 to the 0 is always equal to 1. In fact, anything to the 0 power is equal to 1. Do you want to plug in a couple more of these? You should be plugging in 1. If you plug in 1, you just get 2 to the 1. Of course, 2 to the 1 is 2. And if you plug in 3, now be careful, that's not 2 times 3, but that's 2 raised to the 3, which is the same as 2 times 2 times 2. Take this table of values and graph it. I'd like you to see what the graph is going to look like when we have exponential growth. Now you should get a pattern that generally is in this shape. If we connect the dots, we will get a graph that shows this type of change. Does it look familiar? It kind of looks like the graph you got when you folded paper. Well, that's because every number in this table is twice the number before. If you go from point to point, you're always gaining twice what you had before. You see, this is just like folding paper where you double the thickness. And we can say that the percentage, which was that 1 plus r, is going to equal that base of 2, which means that r would have to equal 1. What that means is 100%. R is equal to 100% growth. In other words, you gain what you had before. Now, there's also a phenomenon that's occurring on this graph that would represent a value that we're never going to reach. And that value that we're never going to reach is an asymptote. Now, they are usually denoted by a horizontal dashed line. And we also label the value of that line as y equals 0. Now, if you think about it, this graph will continue to go to the left, but as it continues to go to the left, it's never going to reach the value of 0. It's always going to be a little bit above it. So an asymptote, or a horizontal asymptote to be specific, for this function, it's a line that we approach, but we never touch, or we never cross, to use a little bit of a different word here. All exponential functions will have horizontal asymptotes. And we like to describe this behavior using an infinity concept. Now, if you will think about this with me, as I go to negative infinity, that means I'm just going to the left. Now, the left would be everything that's happening over here. That's the same as negative infinity. And what we can say is that the function is approaching 0. The function is approaching that height. And so as x goes to negative infinity, which means to the left, the function is approaching a y value of 0, which notice is the same as the horizontal asymptote. Well, that's exponential growth. That's when your equation is going up. But what about if the equation is decaying? What about if the equation is going down? Well, that's going to happen when your base is less than 1. It'll also be greater than 0 because we won't want to have a negative base. So if the base is less than 1, we have exponential decay. Now, we can also think of the base as equaling 1 minus r, where once again r is the percentage. But notice here that we use a minus sign because you're going to discover we want to be less than 1. Now, as long as we have a base that's less than 1, we'll have exponential decay. So how about the base of 1/3 to the x? Notice again that x is in the exponent, and as long as x is in the exponent, we have an exponential function. But this time it's exponential decay, so we're going to be plugging in these x values. If you plug in an x value of -3, you get 1/3 raised to the -3. Now, once again, it's a negative exponent, which is kind of strange, but whenever you have a negative exponent, you always want to flip the base. When you flip the base, you get 3/1, but now the exponent becomes positive. Well, 3/1 to the positive third power is like 3 times 3 times 3. That's going to be 27. I already plugged in -2. What happens when you plug in -1? Well, that would be like having a negative exponent, so we have to flip the base. It flips to be 3/1, but now the exponent becomes positive. Well, that's nice because that just works out to be 3. Remember, we talked that anything to the 0 power is 1, so it still works here. And it looks like we need to plug in 2. Now, when you plug in 2, you get 1/3 to the 2. That's like 1/3 times 1/3. Well, 1/3 times 1/3 is 1/9. We have a table of values. What I'd like you to do is I'd like you to graph it. And as you graph it, you should notice a pattern that represents exponential decay. Now, you won't be able to graph negative 327, but you would know that that point would be way up here. And so as you start to connect the dots from way up there, and you turn quickly, at the bottom, you get a graph that represents decay. It should look kind of like your M&M graph. It should look kind of like the bouncing ball graph. Now, there is a value that this graph is approaching, but never going to touch. And once again, that's going to end up being an asymptote. And we like to label that asymptote with a dotted line, and also its value in this case to be y equals 0. Now, this graph is decaying based on the base. Remember, the base was equal to 1/3, but 1/3 can also equal 1 minus r. The question here is what r value would give us 1/3? Well, that r value would have to be 2/3, which is the same as 66%. So in this case, we would say this graph is decaying by 66%. What that means is that each point, as we go point to point, is losing 66% of what it had before. Now, as far as the asymptote goes, as we talked, we want to use the infinity symbol again to describe that. Here we say x is approaching positive infinity would mean to the right side of the graph. And all we got to do is ask, what is the graph doing? And once again, the graph is approaching the height of 0. So as x approaches infinity, which means going to the right, the graph is approaching 0, which would be that asymptote. So exponential growth, exponential decay, they kind of look similar, don't they? But one of them goes up and one of them goes down. And of course, that's all based on the base being either greater than 1 or less than 1. Now, something we like to do to kind of add to this discussion is to think about some of those common math ideas. If you look down here, we have the domain and the range. Let's do that for each of these. We're going to do the graph analysis for the exponential growth graph. It turns out that the domain is all real numbers because you can plug any number you want in for x as the exponent. But the range, notice, is above the asymptote. So the range is all numbers greater than 0. Now, an exponential growth graph is always increasing. It's always increasing because it's growing. But, of course, it's never decreasing because, again, the base is greater than 1. Now, as x goes to infinity, that actually would be talking about the right side of the graph. So don't be confused here. I did mean that on purpose. The graph looking to the right goes up to infinity. But as x goes to negative infinity, that would be the left side of the graph. And as we already discussed, that would be the part that's approaching the asymptote. Do you think you can analyze this exponential decay graph? I encourage you to think about it, and then we'll fill in the answers. You should have discovered that the domain was the same. You can plug any number you want in for x. The range is also the same. The graph is always greater than 0. This graph is never increasing because it's always decreasing because the base is less than 1. Now here, if you look at the right side of the graph was approaching the asymptote of 0. But if you look at the left side of the graph, it was going up to infinity. Next, we want to look at how the actual value of the base affects the growth of your equation. I'm sure you can see that each of these bases is greater than 1, but notice that some of them are bigger than the other. 2 to the x compared to 3 to the x compared to 13 over 3 to the x. Make sure you interpret 13 over 3 as 4.33, still a number that's greater than 1. We'll take a look at the way that they graph on a calculator. So I carefully typed all 3 of them into the calculator. Let's see what they look like when they are graphed. Now the first one, this is y equals 2 to the x. It looks very similar to our growth equations we've drawn. But here comes 3 to the x. notice that it grows more quickly. And lastly, 13 over 3 to the x, well, it's steeper than all of them. So it looks like as the base gets bigger, the graph grows more quickly. Let's make a nice sketch of our observation, where first we have y equals 2 to the x, which is kind of our parent graph, followed by 3 to the x. Now 3 to the x grew a little bit more quickly, so it's a little steeper. And then, of course, we had our 13 over 3 to the x, which was the steepest of the bunch. Now, it's definitely true that as the base gets bigger, the graph grows more quickly. But did you notice that there's actually something that's the same about all these graphs? That's right, the y-intercept. Now, the y-intercept is what we call the starting value. And that starting value is the letter A, which is in front of all these bases. So, what number is in front of each of these bases? Well, it's the invisible number 1. And that invisible number 1 is serving as our y-intercept for each of these equations. Now, there's one more thing that's true about all these equations, and it's going to be this ever-famous asymptote. The asymptote is the line that our graph is approaching, but is never going to cross. And so we see that the asymptote is 0 for all three of these. Now, just one more time, I wanted to talk about this percent growth idea. Sometimes students get a little confused what I'm trying to say. And so remember, the percent is the letter R, and it would be found by thinking of the base, which is 3, equaling 1 plus R. So simply, if 3 has to equal 1 plus R, then there's no doubt about it that R equals 2. So what is 2? Well, 2 simply represents the percent, not 2%, but 200%. That's because 2 is really the number 2.00, which in percentages is 200% growth. How about the base affecting a decay problem? Now here we have, once again, 3 different bases that are all less than 1. But notice that they are of a different size. So, what happens as the base that's less than 1 changes? So once again, I typed all these into the calculator. Let's see what they look like when they are graphed. Now here's 1/3 to the x, a nice decay graph. But 1/6 to the x, well look, it is actually decaying faster. Now 0.7 to the x, it doesn't seem to decay as quickly, but it still goes down as all three of these bases are less than 1. So all 3 graphs represent decay, and if we're going to sketch what we saw, this might be our 1/3 to the x graph. But the 1/6 to the x graph, 1/6 was actually a smaller number. And so because the number is smaller, the graph actually decays more quickly. The graph is steeper compared to 0.7 to the x, which is less than 1, but it's not as small. And so when we look at something like 0.7 to the x, we see a graph that still goes down, but does not go down as quickly as the others. Now, are you catching on? There's something that's the same about all these graphs. That's correct. It's the y-intercept. And once again, that's the number A that is in front of each of these bases. Now, if you're saying, Ms. Naylor, is it always the number 1 that's in front of a base? It is not. We will find out in a moment that we can start to change that number. But before we do that, we still have an asymptote, and the asymptote is the line that our graph is approaching but is unable to touch, and all 3 of these are approaching 0. To discuss this percent idea one more time, are you catching on to that? The percent is just the number R, which can be found by thinking that the base would be the same as 1 minus R. Now, the reason it's 1 minus is because these numbers are less than 1. So we have to ask ourselves, what type of R value could we subtract from 1 to get 1/6? And the answer, of course, would be 5/6. Now, 5/6 would be the rate, which is the same as 83%. What that means is that 83% decay is the same as having a base of 1/6. And so we want to be careful that we don't say that the base is the percent, but rather we can find the percent by thinking about subtracting from 1. Now, as we flip to the next side, you'll see that we're ready to start to think a little more about this letter A. And the letter A is the number that's in front of the base. So you can see that we're clearly going to multiply by a different number, 2, or a different number, 5. Now, before we look at that, I just want to make sure that you're still aware that we have some things that we know. We know that this base is going to represent growth. So we expect to see a graph that's going up. And we know that this base is going to represent decay. So we expect to see a graph that's going down. So now, what is going to happen when we have a number that's being multiplied in front of these bases? All right, so we got our equations typed in. Now, the first equation is growing, as we expected. The second equation is decaying, as we expected. So now the question is, where do we see the number 2 in the first equation? Well, look carefully. It's the y-intercept. And in the second equation, where do we see the number 5? Well, look carefully. It's the y-intercept. So let's sketch our observation, but this time I want to very carefully mark that letter A as being my y-intercept. So we know that 2 would have to be the place where this graph is going to pass through as it goes on its way growing. And just the same, we can say that the letter A, which is 5, is going to be our y-intercept. And that'll be a nice point that we can use as we draw a graph that is decaying. So what is happening here is we're starting to see that we can transform these exponential equations. And the idea of transformations is one of those big ideas that we've been studying all year in Algebra 2. Transformations, remember, are any time that we change or shift or reflect a graph. And it's always good to remember how to do this with an old graph, like maybe a parabola, so that we can do this with a new graph, our exponentials. So remember, you see this negative sign here, and I hope that you would say that this graph reflected down. It reflected down over the x-axis. You see a number in front that is greater than 1, and you should say that this graph stretched. It's stretched vertically, and we always have these shift numbers. The one that's on the inside is always going to be a horizontal shift, in this case to the right because it's a minus sign, and we see this number on the outside. We see this number on the outside, and that has always been a vertical shift. In this case, it would have shifted down. Now, let's take these same transformations and let's apply them to the exponential equation ab to the x. So if we add to the end of the function, that is always going to cause a vertical shift. If we add to the end of a function, it's going to take the points of the graph and shift them vertically. But you see, it's also going to shift the asymptote vertically, which means that k will become the value of the new asymptote. K will be the value of the new asymptote. So if we have an equation like 2 to the x plus 3, how can we use transformations to come up with this new graph? Well, first and foremost, it's definitely true that this graph has shifted up 3. And since it's shifted up 3, we can also say that the asymptote is going to equal 3. Now, the number 2 is the base. And we want to be careful that we only use the base to determine that this graph is going to grow. Remember, since the base is greater than 1, this is going to be a growth graph. And lastly, we have the number that's in front of the equation, which in this case is still the number 1. Well, remember, that's the starting value. So the graph is going to start at 1. So how do we draw a sketch using this information? Well, first, if our graph is going to start at 1, we can think about that point, but we only want to use that point as a reference for our shift. You see, from the number 1, I'm going to shift up 3 more. Now, if I shift up 3 more, What point am I at now? Yes, I am at the point 0, 4. So our y-intercept, it might have started at 1, but it then shifted up 3 to get to the number 4. How about our asymptotes? Well, the asymptote is going to be at 3. So we can draw a horizontal line and label it as y equals 3. The only thing left to do is to draw a growth graph. And all growth graphs are going to have the same basic behavior where they pass through the intercept as they grow up to infinity. And don't forget that on the left side of the graph that we are going to be approaching the asymptote. If you add or subtract a number to the inside of the function, that is, if you add or subtract to x, that's always going to cause a horizontal shift. So all the points of the graph are going to shift horizontally. Take, for example, 2 to the x minus 2. Now, you have to interpret this as the minus 2 being on the inside, being right beside x, which means that this is going to end up being, since it's a minus sign, it's going to end up being a shift to the right. Now, we also have the base. Remember that all the base does is it determines if it's going to be growth or decay. Once again, we have a number greater than 1, so it's a growth equation. How about the starting value? It's the number in front of the base. Once again, since it's not shown, we have to assume that it's the number 1. Now, there's one more number that's not shown. It's the number that's at the end of the equation. Well, since there's no number that's shown at the end of the equation, we would have to say that it's plus 0. And so plus 0 will end up being our asymptote. So how can we draw a graph that has these transformations? Well, just like before, we can start at a y value of 1. But remember that you're only starting at a y value of 1, so you can shift to the right 2 more units. Now, where would you be if you started at 1, but you shifted to the right 2? That's right, you would be at the point 2, 1. You would be at the point 2, 1. Now, that point is not the y-intercept, but what we call it is a shift point. How about the asymptotes? That asymptote did not move. An asymptote does not shift horizontally. It can only shift vertically, so the asymptote is still at 0. The only thing left to do is to draw a growth graph. And all growth graphs are going to have the same basic shape where they pass through that point as they go on to infinity. And of course, back here on the left side, they approach the asymptote. If you multiply a number to the front of a function, we've already determined this year that that's always going to either stretch or compress the graph. If you multiply a number like a to the front of a function, it's always going to stretch or compress the graph. But we've also learned in this unit that a becomes what's known as the starting value. And so a can actually change 2 parts of the graph. It changes where it starts, and it also changes its stretch or compress. If you take this example 6 times 1/2 to the x, we clearly have a new a value. Now that new a value is going to do 2 things. It's actually going to determine that this graph is going to start at 6. But because 6 is a stretch number, we're going to end up with a graph that looks steeper, that looks more stretched out. Now, what about this base? Well, as I've said many times, make sure that the only thing you do with the base is that you use it to determine that the graph is growth or decay. In this case, I hope you determine its decay as the number is less than 1. Now, there's no other numbers added or subtracted, so we don't have any shifting. So we want to make sure we understand that the asymptote is still going to stay at 0, and we can use that as we come up with our final graph. So the graph starts at 6. It actually turns out that it not only starts at 6, but it stays at 6 because there's no more shifting. The asymptote is still at 0, so we can label that. And all we really have left to do is draw a decay graph that has been stretched. Well, a decay graph that has been stretched is going to decay very quickly. It's going to be very steep, and it's going to at the very end, turn and approach the asymptote. Now, if you put a negative sign in front of a function, that is always going to cause a reflection. It's always going to cause a reflection down. And we like to say that that would be the same as reflecting over the x-axis. So what's an exponential function going to look like with a negative sign? Well, first we see that it's in front of the function, and since it's in front of the function, we have a reflection. We definitely have a reflection down over the x-axis. We also see here that we have a base. As we've said many times, the base is only going to determine the growth or decay. But you see, when there's a negative sign in front, that also would be like an a value in front. And the a value is the starting value. So yes, this graph is going to start at -1. Now, when you draw something that's reflected, sometimes it's helpful to first think about the graph before it was reflected. And a growth graph that before it's reflected has always had this same basic shape. So what we want to do is we want to think about what would it look like if it now flips down. Well, if it flips down, it's going to end up starting at -1. So we can draw and we can label -1 as our y-intercept. And of course, it's going to then have to have a shape that is a reflection, that is now reflected down over the x-axis. Now be careful, sometimes students will say, oh, so this is a decay graph. Actually, no, it's not a decay graph. It's more correctly described as reflected growth. It is reflected growth. Still has an asymptote though, doesn't it? And that asymptote did not move. It's still going to be at 0. Now we have one other kind of reflection. That is if we put the negative sign right on x. Now if we put the negative sign right on x, it's going to be a reflection sideways. It's going to be a reflection horizontally. We would say that it's reflection over the y-axis. So what's an exponential equation going to look like with a negative sign on x? Well, take a look. You can see that the negative sign is in the exponent. Now, if the negative sign is on x and it's in the exponent, this is going to be a reflection over the y-axis. If we think about some of the other parts of this problem, there still is a 1 that's in front of it, so we still have that starting value. And don't forget about the asymptote. It would still be at 0 as that number is not shown. So, oh, and of course the base. The base, as we've seen many times, is greater than 1, so it's going to be a growth graph. So what is a reflected graph going to look like that was once growing? Well, it might be helpful to think about a graph that was once growing, and if you reflect it over the y-axis, you want to feel like that it's kind of spinning on a swivel. That is, now the graph is going to be going in this direction. Wait a minute, this direction is a decay graph. So if you reflect the graph over the y-axis, it actually flipped the growth graph, at least what was once growth, it flips it to be decay. Now, why is that happening? Well, keep in mind what's true about any negative exponent, because anytime you have a negative exponent, in this case 2 to the negative x, that would be the same as flipping the base and having a positive exponent. And looky what you have now. You have a base that's less than 1, which we know will be a decay graph. Don't forget about the asymptote. I'm sure you didn't, but you always want to label the asymptote, and that's still at 0. Now, the whole idea is to use transformations to be able to make a nice quick sketch of this exponential equation. And honestly, you can look at these numbers in any order that you want. I tend to look at this number first, and that's going to cause me to conclude that we definitely shifted up. It also would help me to be able to identify the asymptotes. Maybe the next number you see is the base. Make sure that that base does what it always has done. It just tells you if it's going to be growth or decay. And I guess the only number left for us to talk about is the number in front. Now, the number in front is an interesting number because it does do two things. Because that number is greater than 1, it stretches the graph. But it's also going to cause the graph to start at 1. And so we want to try to put all these ideas together, which really, the first thing we want to do. Now, the idea here, just like we've done all year, is to use transformations to be able to make a nice quick sketch of an exponential graph. So we can look at these numbers in any order that we want. It really doesn't matter. I tend to like to start with this number out here. It's very clear that the graph has shifted up based on that number, and it also actually creates the asymptote to be at 1. If you're looking at the base next, you would definitely conclude that because the base is greater than 1, that this is a growth graph. And then we get to our, in this case, the last number we're looking at, but the first number in the equation, which is the a value. Now remember, the a value is definitely going to be where the graph starts, but it also is going to change the stretch or compress of the graph. Remember, if the number in front is greater than 1, then it's a stretch scenario. So what do we have? We have a graph that starts at 3, but it doesn't stay at 3, right? It shifts up 1. Now, if you start at 3, but you shift up 1, you have to be able to conclude that you are now at 4. And you want to label that point because that truly is the y-intercept. What else do we have? We have an asymptote that is at, that's at 1. Okay, so it's going to still be sort of down here. Yes, the asymptote is at 1. And the only thing left to do is draw a graph that is growing but is stretched a bit. Well, the only way to make a graph approach that asymptote but stretch up to that intercept is to draw it a little bit steeper. And so we have a really good sketch of this equation. Now, I'd like to add to this what I call the y-intercept check. And the y-intercept check is simply understanding that a y-intercept is always when x is equal to 0. So if I plug 0 into this equation, I can find out by some arithmetic that my y-intercept is going to come out to be, well, let's do some arithmetic because 2 to the 0 is equal to 1. You always do exponents first, right? So now we have 3 times 1 plus 1. And, oh yeah, that is going to come out to be my y-intercept of 4. So we just do a little arithmetic check to make sure that our graph is right. You want to try one on your own? I encourage you to look at all the numbers in this equation, try to decide what transformations they would be, and then see if you can draw the graph. Okay, how's it going for you? You can check any of these things as you would like. That minus 3 is going to cause the graph to shift down 3. It's also going to make the asymptote be at negative 3. Now this minus 4 is going to actually shift the graph to the right 4. It's going to shift the graph to the right 4. Make sure that the 1/2 is only being used to say that this is going to be a decay graph. Remember, if the base is less than 1, it's decaying. Looks like we're back to the invisible a value. That means that the graph is going to start at 1. Can you take all this information and can you come up with a sketch? You want to start at 1. Now this graph has 2 shifts. It actually shifts to the right 4, and then it continues to shift down 3. You have to do some careful counting, don't you? So where am I at? If I started at 1, I went to the right 4 and down 3. You should be concluding that you're at 4, negative 2. Now, there's never a bad time to put the asymptote in the right place. The asymptote is down here at negative 3. You might as well get it on there. That is a guarantee. What does it seem like we're missing? It seems like we're missing the y-intercept. Now, the thing about the y-intercept is that it was not found by shifting. So maybe we could find it by some arithmetic. You see, if you plug in 0, like you can always do for a y-intercept, if you plug in 0, you have yourself a little math problem you can work out. And it turns out that 1/2 to the -4 is the same as 2 to the +4. Remember, all you have to do is flip the base when you have a negative exponent. Now 2 to the +4 is the same as 16. And of course 16 minus 3 is 13. Now that was a little bit new, but what that does is that allows us to mark a point on this graph as a y-intercept, specifically as 0, 13, where we can draw a decay graph that passes through these points as it approaches the asymptote. Now, the last thing we want to do with the ideas we've learned today is think about using these transformations backwards, to write equations. A lot of times we like to think about writing an equation using the same concepts. Now, in the case of this, it's kind of neat because we can just build off of an equation that we are given. So if we're given the equation f of x equals 4 to the x, and it says, well, that it's been reflected, then I can take that equation and start to add some things to it. Now, if it's been reflected over the y-axis, we know that we're going to have to add a negative sign to the x. What else can we start to add here? It says that there's been a stretching of a factor of 3. Well, that's just going to give us a number that we can multiply in front of the base. Now, be careful. You never want to take that base, you never want to take that a value and multiply it to the base. So we don't want to end up getting the number 12 right here. Rather, we want to see 3 times 4 to the negative x. Well, the last thing I hope you see here is that we have an asymptote. And that asymptote is just going to cause us to put a -7 at the end of this equation. So you see how we just kind of built off of what we were given? Now, this would be an interesting equation to graph, but let's just do one thing at a time. It looks like that we have an asymptote at -7, so that definitely can be drawn. It looks like we have a starting value of 3. Now, if we have a starting value of 3, we just want to make sure that that's not where we end up, because if we start at 3, you actually have to shift down 7 from that point. So that's actually going to give us a final resting point of -4, and the only thing left to do is think about the shape of the graph. Now, the shape of the graph sometimes can be the most complicated thing, because you look at the base 4 and you say that's going to be a growth graph, right? Well, not after we reflect it. You see, if I had a growth graph, it would be going up, but this graph has been reflected, so it actually ends up going down. It ends up being a decay graph. Do you want to try to do letter B on your own? Now, if you build off of what you have, you would be able to take the 1/2 to the x and definitely subtract 3 as it's shifted to the right 3, but notice that that is up in the exponent. And then we can shift up 2 units. We're going to put that at the end of the equation. That's all we got, but I thought I would have you think about the y-intercept. Why am I having you think about the y-intercept? It's going to be an important number to know when it comes time to graph this equation, if I can get this set up right. Now remember, all you got to do for the y-intercept is plug a 0 in for x. You can stick with the rest of the numbers that you have. This actually ends up giving us a negative exponent. Now, I don't like negative exponents either, so what you do is you flip the base, you make the base 2 over 1, and the exponent becomes positive. That's good news, because now we can do 2 to the 3rd power, which is 2 times 2 times 2, and we get a y-intercept of 10. And that's going to be a helpful number when it comes to graphing this equation, because you can be guaranteed that the y-intercept is at 10. We can label that. What else do we have? Well, we have to be careful, because what we have is a starting value of 1. And you see that starting value of 1 is where I'm going to shift to the right 3 units, and then I'm going to shift up 2 more. So again, some careful counting is going to lead me at what final point? What final point? We would have to call it the point 3, 3. Okay, we went to the right 3, but we went up 2 more, so we're now at the point 3, 3. All right, well, we said that the asymptote is at 2, so we can get that on the graph. And as long as you're comfortable that this is a decay graph, you'll be glad that you can draw a graph that goes down as it passes through these points and gets close to your asymptote. Now, there's definitely been a lot of new information given today. Make sure that you carefully think about the homework. Make sure that you go back through your notes as you carefully think about the homework. And your goal is to get these right. In fact, when I check your answers, I'm going to be checking 2 of these problems randomly that you have them fully correct. So work towards correctness as you keep learning about exponential growth and decay and transformations.